I do not have your exams back for you today, so you will get them back for sure this coming Tuesday, barring any extenuating circumstances. You can get them back then. And otherwise, I have posted your homework 7 for you to be due a week from Saturday, I think. Whatever it says in there, do that. And then your homework 6 is, of course, due today. So hopefully you've been able to restrain yourself from using too many of these energy techniques that I've been talking about Tuesday, and we'll talk more about today, and have used the quote-unquote work method for the back half of that homework. Because as we'll see today, being able to calculate a work the old-fashioned way is a very useful skill. We sometimes still do need it, so it's important to be able to do that. Okay, any questions, admin, logistical, stuff like that before I get started? What to expect? Okay, so I anticipate I will be able to finish homework number 7 material today, so I'll let you know when that hits. Let's go ahead and get started. So last time I started with comparing and contrasting two common forces we need to contend with, gravity and friction, and we find that there's a big difference in how they behave. This is a side view of a ball flying up into the air, and we saw that as the ball rises, gravity does negative work, removes kinetic energy, but when it falls back down, gravity will do positive work and add that kinetic energy back. So you put the kinetic energy somewhere, and then you got it back from there. That's why we call where it went potential energy. Potential energy makes sense. Potential meaning stored. So you can say that energy gets stored if you can get it back from storage, and that's exactly what happens. By the time it falls back down, it's going the exact same speed as you threw it. With friction, it doesn't work like that. So if this is a top view of something sliding along a flat surface, friction will do negative work and take kinetic energy away from it, so it slides to a stop, and it certainly does not come back spontaneously. That's why I crossed this out. Because the kinetic energy is stolen, it's not in storage, it's just gone. I'll talk about where it went in just a moment. And if I were to push it back, which is to say give it some more kinetic energy, friction would still act. Friction always does negative work, because friction is always against the motion. So trying to just say there's a potential energy due to friction, that makes no sense. Okay, you can't say that the energy is stored if it always takes and never gives back. The whole point of storage is that it's a reversible process. So, what do? Here's the approach we're going to take. Let me write down some energy forms. Kinetic energy, that's of course the first energy form that we talked about. It's kind of like the grand central station of energy forms. All the signs are defined in terms of inbound or outbound. So, a positive work, for instance, the work done by gravity, if that's positive, if it goes in, it's negative if it goes out. So another form of energy, of course, let me put that energy bank account in there. There's another form of energy, and that's a two-way street. But here we have thermal energy. And that is not a two-way street, that's a one-way street. So the work done by friction is always negative, and it can never be positive. So that's why I just call that thermal energy. I don't try to say it's potential energy or something like that, because it's not really potential if it's just there and you can't get it back. So think of it like you have all these different energy accounts, and there are some that you can freely transact with both ways, and then there are others where there's a one-wayness to that transaction. It only gets called a potential energy if it's a complete two-way street. If anything you put there can be retrieved. If it's a one-way street, it's another form of energy, but we don't call it potential energy. Okay? So the question is, how are we going to incorporate this idea into our energy method? We're going to have to, in some ways, cut our losses in terms of this idea of energy conservation. We would ideally like to come up with all these different boxes of energy and just say the sum of all of them is constant. That's just saying energy cannot be created or destroyed. But the reality of it is that energy can come in so many different forms, and we can't chase them all in this class. We don't have the means to do that. So at some point we just cut it off. So what we do is we group the certain energies that are easy to contend with. These are the energies that are nice, they trade amongst each other, okay? Think of that bubble there within the dotted line, that's like our house, okay? That's the physics 1 house, okay? So in here, physics 1. Or more generally, just energy forms that can freely trade amongst each other without any complication. Kinetic energies and potential energies only. They're the only ones that are invited in. It's like you wouldn't want to have a roommate that only takes your food and never gives you any food, right? Okay. So we're going to call this bubble here, all the energy forms in here, we're going to call this E. But E now no longer stands for total energy, because we are now acknowledging that there are some forms that we don't want to mess around with. This is called mechanical energy. And only includes kinetic energies and potential energies. We only have one form of each so far, but we'll have several more of each kind by the end of the class. Okay? So E now, you have to understand, its designation is no longer every single type of energy possible. It's a particular subset of energies called mechanical energies only. Okay? And when we go over here and compare gravity versus friction, gravity is an example of what we call a conservative force. When we say conservative, I don't mean it conserves energy, because there's no such thing as a force that can destroy or create energy. What we actually mean is conservative of mechanical energy. So we have that the sum total of what's in the bubble here stays the same. So gravity converts between these two, but the total inside won't change. Friction is an example of what's called a non-conservative force, which we often abbreviate NC. And when we say non-conservative, we don't mean of total energy, because there would be no such thing as a force that could create or destroy energy. What we mean is non-conservative of mechanical energy. You can see that friction takes energy out of the bubble to some other stuff. Okay? So let me say a few brief words about what's going on here. This gives me a chance to perhaps tie into some of your Gen Chem stuff. Why are certain forms of energy conservative, why are certain forces conservative and others non-conservative? In other words, why is it that some energy forms can be freely traded with back and forth, and why are some more one-way streets? So the difference between mechanical energy and non-mechanical energy, one of the ways that you can describe it is that this is macroscopic energy and this is microscopic energy. Okay? So anytime you cross over the threshold between macro and micro, you have some issues. Let me explain. For instance, when we talk about the kinetic energy of an object, what we are really saying is that all the atoms in the object are coordinated. So we're saying that the object as a whole is doing something because everything is doing that. However, if this slides along a friction surface and stops, we of course say, well, the block stops so the kinetic energy is 0. Well, it's really that the kinetic energy of the block as a whole is 0 because it's gone from kinetic energy to thermal energy, which is really like another form of kinetic energy, really. It just means that those atoms are wiggling around faster. So we've taken the energy that's coordinated and we've uncoordinated it. And once you've taken energy and uncoordinated it, you can't easily coordinate it again. There's something that's working against you. There's a phenomenon called what? Entropy, okay? So when you're crossing over between the macro and micro, you have to contend with entropy. So for our purposes, we acknowledge that anytime you cross this barrier, it gets more complicated. Now, we're not going to be calculating entropy or anything like that here. You'll learn how to do that in chemistry. But the point I just want to make is that once we have uncoordinated that energy, so that rather than the whole block moving together, we've taken that energy and we've shunted it down into the microscopic level, for our purposes, it's going to be gone, okay? So on the macro side, we have kinetic energy and potential energy. Those are things that have to do with the motion and location of the whole object, right? So this is for the entire object. We can talk about the entire object's speed, the entire object location, things like that. We can talk about the object as a whole. We don't have to talk about what's this atom in the object doing versus this other atom. So for us, largely, this is just concept only, okay? So we just acknowledge occasionally we will either lose some energy across this barrier or gain some energy across this barrier. I'll show you an example where you gain it in just a moment. But for our purposes, it's kind of, we're staying mostly in the bubble. It's just, we just want to acknowledge that if the mechanical energy changes, it's not a violation of the conservation of energy. It simply means that we've taken energy to some other form which is inconvenient for us to deal with. Okay, so we kind of just say it left. Okay, so how do we take care of that? We just build it into the energy equation. So what we do is, here's our energy method in a final form. It looks like this. So, at this point, we understand that E is just kinetic energy and potential energy. It's not all forms. It's just these particular ones. We understand how to compute them. They have to do with the object speed and location. We have formulas for that. They're all firmly in mechanics, okay? And we can tally that up at the beginning. We can tally it up at the end, but we won't always get the same total. And that's okay, because that means that there is simply the presence of some force that's inconvenient to contend with doing non-conservative work. Okay? So for example, if your non-conservative work is negative, you're going to get E initial plus some negative stuff, so the final is going to end up smaller. So when we do our tally of kinetic energy and potential energy at the end, we won't get as big of a number. Doesn't mean it got destroyed. We can conceptually say, where did it go? One example, for instance, is friction. Friction does negative work, and it transfers to this energy form that's inconvenient, so we simply say it's gone for our purposes. So an example would be friction. So think of this as kind of built into the equation as like an in and out valve to other energy forms that are inconvenient for us to deal with right now. So that's like, think of that as the in and out valve to other classes, right? That's going to be how we treat this. We just have an ability for energy to come in or go out so that we can contend with it. But we're really going to just keep track of kinetic energy and potential energy. Okay? of course, there's a possibility that there is no non-conservative work. So maybe there isn't something in some kind of force that is inconvenient here. In that case, you'll get what we were doing all of last lecture, which is we will be lucky enough to see that all the mechanical energy is still there. So the energy stays mechanical completely. We don't have to worry about any weird other energy forms. It could also be not just that energy can flow out in this manner, it can also come in to mechanical this way. In which case, when you tally up your mechanical energy at the end, it's going to be more than it was at the beginning. Let me give you an example of that. So let's say I take this eraser, all right? I'm going to put it on the table, just because I don't want to bend down to the floor. Okay, let's say this is the 0 height, okay? So how much potential energy does it have here? Gravitational potential energy. What is it? 0. If I decide that 0 is here, then that's 0. Okay. If h is 0, then mgh is 0. Okay, 0 potential energy. How much kinetic energy does it have? 0. Okay. So 0 mechanical energy, right? I'm going to put it up here. How much kinetic energy does it have now? Still 0. How about potential energy? Has some more. So what happened to its mechanical energy overall? It went up. Okay, where did it get that energy? How did it get up there? Me. I gave it that energy. Where did I get it? Got it from the frosted flakes I ate this morning. Okay? Okay, I need to eat. Okay? So we have another example where we are having, on a microscopic level, I'm breaking the chemical bonds of the foods that I eat, and I'm passing it up to more potential energy for that eraser. So once again, we're crossing over this barrier. And you probably know that if I get hungry lifting that eraser up there, okay, I'm not going to get full again by putting it back down. Okay? That is not a two-way street. It's not just a trade. So we have chemical energy. That's another form of energy we don't want to really mess with in this class. It is just a source of somewhere to get energy. So for instance, I could do my pushing force in that case. Did positive work. Now in this case, it didn't of course go to kinetic energy. I could do that too if I threw the eraser really hard, right? I'd be giving it a lot of kinetic energy. But because I was lifting it vertically, gravity has the nature of saying, yoink, I'll take that, I'll put it over here. Okay? So we had the chemical energy, kinetic energy. It didn't really gain any kinetic energy. It just kind of passed through up into potential energy. So it started off with no potential energy and ended up with some when I put it up higher, right? So again, not a two-way trade. Okay? If I lift something, I use chemical energy. If I lower something, I also use chemical energy, right? So the problem is anything that isn't a clean two-way street, anything that crosses the macro-micro barrier, I'm not going to try to mess with it except for, in this case, use it as a source of energy. So if I tally up my energy at the end, and it's more than at the beginning, I shouldn't panic that I've suddenly created energy out of nothing. I should probably acknowledge in some way where it came from, but I'm not going to try to do it more than that, okay? So I'm not going to try to calculate, for instance, how much of my Frosted Flakes intake was required to lift that, okay? So it's just conceptual only. Okay, so that right there kind of encapsulates our approach to energy in this class. We stay tallying up the quantitative formulas for kinetic energy and potential energy, collectively called mechanical energy, and occasionally we have energy leaving or coming in, which we acknowledge conceptually only. So that way we can understand that energy is conserved, right? Total energy is always conserved, But that doesn't mean that we always want to track every single box individually. Sometimes we have to let something go and just say, we're not going to get a formula. So we know the formula over here is mgh. We know the formula right here is 1/2 mv squared. That's how we keep track of the balances in those things. We're not going to address what's the formula for this, what's the formula for this. Generally, this is the wild woods of other energy forms. We got to call it a day somewhere and just leave it concepts, okay? All right, so before I do an example incorporating one of these, questions? Yeah? Correct.
Did you say that it also had some, it had potential energy?
Yeah, because once I've chosen the 0 to be here,
Okay.
if I lift it higher than that, it's going to have some mgh, right? So that's, I should mention, it's very different from gravity, right? If it's talking about gravity only, right? If something's going to go higher, it has to have something to trade, right? So if it goes to higher potential energy, it goes to a lower kinetic energy, right? So there, it's just trading between the two, right? So as something goes up, it slows down. As it comes back down, it speeds back up again. What I was talking about was lifting it to a higher height and more potential energy, but it was not at the expense of the kinetic energy, because the kinetic energy was 0 to start with and 0 at the end, so it's not like I gave one to the other. In fact, overall, those two, the sum total of these two increased, right? So there's a big difference between these two trading, but this being constant, versus in my situation, this one increased, but this stayed constant. So this had to increase, right? Okay. Any other questions before I do an example? Yeah.
Are we going to encounter issues where there are other non-conservative forces, but they cancel out to get 0? Where it's not like just not a factor, but you have some friction and some chemical energy or something, and then...
Well, so in our case, remember that we usually compute the work done by each individual force. So we usually don't combine forces, right? Because if you start combining a series of forces, some of which are conservative and some of which are non-conservative, then your net force, that's going to be, well, it's going to be non-conservative. If it has any non-conservative ingredients, it pollutes the whole batch, right? So we don't generally do that at all. What we're doing in this approach is taking each individual force, calculating the work. Some of them will be conservative forces that trade just between these. Some of them will be non-conservative, which trade outside of the conservative.
So it would only ever be one non-conservative element?
Well, there could be more. I mean, I could give you a problem where you had both of these. So you're putting energy in and friction's taking some energy out. So you, that's perfectly fine. That's why this is non-conservative, because anything that's non-conservative gets put in there. You can have the work done by the pushing force. You can have the work done by friction, maybe both. But what you would never include, of course, here is the work done by a conservative force, because that's kind of already operating in the background. That's what's trading between these two. And we don't need to compute it explicitly, because we're just going to sum these two and make sure that they're both accounted for, right? So conservative works transfer between these two, and as long as we account for both of these, we're fine. But anything that trades outside, we need to include it in this term right here. Any other questions? Okay, so as far as actually executing on a problem, it's actually just putting together everything we've talked about so far. We've talked about kinetic energy and potential energy, and therefore mechanical energy. And then as far as computing any of these non-conservative works, this is where you compute a work the old-fashioned way. So that work, no pun intended, that you put in to learn the work method, well, you still have to compute some works the old-fashioned way. It's just only the non-conservative ones have to be computed. So let's take a look. So we'll go back to that roller coaster loop-de-loop example. So I did that last time. We had some roller coaster car that started off here at rest. It was on a hill of height 30 meters. I gave you a loop-de-loop that had a radius of 10. I asked you the speed at points A, B, and C. And now I'm going to add a little bit of an addendum here. I'm going to say that once you go through there, you actually hit a friction patch. So that friction patch, of course, you could get stuck in there entirely, but the numbers I'm going to give you are that it does emerge from the other side. And let me give you the values, make sure that I have these right. The friction patch is going to be 20 meters wide, and it's going to have a coefficient of kinetic